This is a quick video to give you a preview or review of the material that's covered in Chapter 12 per Zoomdal text, Bonding and Lewis dot structures. These comprise one of two topics that you're going to cover on Exam 4, the other one being energy. It will be covered in a separate video. And oh, by the way, if everything that you learn about bonding and Lewis dot structures is a movie, then what I'm going to show you now would be considered a trailer. So with that, let's look at bonding and Lewis dot structures. As you learned earlier, there are two main types of reactions, ionic and redox. On a similar vein, there's two types of bonds, ionic and covalent. Now, a bond is what holds atoms together. An ionic bond is held together by electrostatic charges, that is, opposite charges, sodium chloride, the positive and negative. Well, there's another type, and that's where they share electrons. They're held together by sharing electrons, not by charge. So, let's look a little closer at that. As I say, sodium chloride is held together by ionic bonds. But what holds water together? These are not ions here. These are held together by bonds that share electrons, and those shared electrons are represented by a single dashed line. A single dashed line represents two electrons. Oh, by the way, depending on the two atoms that are being held together, sometimes it takes one bonding pair to hold them together, sometimes two bonding pairs, and sometimes three bonding pairs. You may see as many as three of these dashed lines. Some larger compounds might have both types of bonds, both ionic and covalent. An example would be sodium sulfate. Here you can see the sodium is held to the sulfate moiety by opposite charges, and yet all of the sulfurs and oxygens are held together by covalent bonds. And here's what I was talking about just a second ago. This sulfur and this oxygen are held together by two electrons, and this sulfur and this oxygen are held together by 4 electrons. Nevertheless, ionic and covalent. This chapter deals with covalent bonds. Okay, so let's talk a little bit about bonds. They basically represent the force that holds atoms together. And when you have a number of bonds, they give the molecule a certain shape. And this becomes very important because shape oftentimes determines or greatly impacts a molecule's physical properties. And also within these bonds contain energy. And that's where we're going to head into the next chapter when we talk about energy. So, for example, if you burn ethane in air, you'll get carbon dioxide, water, and what else do you get? You get energy off. We know that from when we burn hydrocarbons. So what this means is the energy of all these bonds is less than the energy in these bonds, and that difference in energy is given off as raw heat or raw energy. Right. So now let's talk about the shape. One of the things we're interested in is polarity. Now, what's polarity? Well, that's is the charge in a molecule lopsided? Because if that charge is lopsided, it begins to act like a magnet, and that gives certain chemical properties. So basically, what is polarity? It's unequal sharing. Right. Now, why that's important, or how you're going to find that out, is through this long thing which I'm calling the NASA protocol. Yes? First of all, let me say NASA, this thing is not it's on Google. It's not in any other textbook. It's kind of an acronym that I made up. It stands for Need, Available, Shared, and Additional. Need, available, shared is discussed, but not in the terms of NASA. So don't go Googling, trying to figure out how to make a NASA table. It's not there. Okay, so here we go. So just so you know in advance, to get to polarity, you have a lot of things you have to go through. This will be one of the key topics of this material. Right now, I'm just giving you bits and pieces of them, and we will go over one of these entire processes here in a minute. But right now I'm explaining to you when we get to the end what polarity is. Okay, electronegativity. To determine how lopsided charge is, the why charge is lopsided is some elements hold an electron much tighter than others. And in other words, you might think of electronegativity as being electron greed. So the most electronegative element, the most electron greedy element in the periodic chart is fluorine. And the least is francium. And you can see those two on our periodic chart here. So what you will notice as a general trend is electronegativity increases going from bottom to top and increases from left to right. So what this means is that fluorine has a greater electronegativity than oxygen, and it's greater than nitrogen and greater than carbon and greater than boron. And likewise, sodium is greater than potassium, is greater than rubidium. So you can see we increase as we go from bottom to top and from left to right. That's just a general trend. So what's the consequence? Well, look at fluorine for a second. Let's consider fluorine and let's consider hydrogen. So they have different electronegativities, and that electronegativity is pretty large because fluorine wants to gain the electrons, and so we say it has a partial negative charge. The electrons are hanging around the fluorine end more. And likewise, hydrogen has less electronegative, so it's kind of sort of positive. And this positive and negative, this difference in electron sharing makes hydrogen fluoride act like a little magnet that has a negative end and a positive end. So these are three ways to represent that. Sometimes you see an arrow where the arrow points to the negative end of the molecule, and the little plus sign here is the positive end. So these can greatly impact the physical properties. Now, if you have two atoms that are the same, they're going to have the same electronegativity, and so our difference in electronegativity, and that's what we're interested in, is 0. So this would be considered nonpolar. Likewise, when the difference gets to be close to 2, that's very polar. Okay. And then if you find something that's about 0.5 difference, it's slightly or moderately polar. Okay. That just gives you a relative sense for these. And by the way, some of these are put to scale. They actually have numbers for these. And just so you know, on the high side, fluorine has an electronegativity of 4.0, and that's as large as it gets. Yes? And francium is really, really close to 0. So that's kind of your relative scale, 0 to 4. Okay. A quick aside here and what we mean by formula unit. Sometimes we say the formula for sodium chloride is NaCl. Well, that's not technically true. This is the formula unit. A salt crystal has millions of sodiums and millions of chlorides, but we don't know exactly how many. Could be a few 100,000, a few million, but we do know no matter what it is, for every one of these, there's one of these. But we can't call it the formula because that's not technically correct. So that's called the formula unit. It's the formula of the most simple repeating unit. It's a technicality, it's a hair, but it's a hair scientists sometimes like to split. So we're just going to call it the formula, but just so you know, when you have an ionic material, it normally has a structure like that. And ionic materials are technically the formula weight or molecular weight is really called the formula unit weight. Okay, on the other hand, water is for sure only 2 H's and only 1 oxygen. There's no other version, so that's why that's not called a formula unit. It's just called the formula. Right, so with that, let's kind of pull this thing together called the polarity spectrum. As I've just introduced you, some things can be nonpolar if they have the same electronegativity. If the difference in electronegativity is small, it's slightly polar. If the difference is really large, getting close to 1.9, it's very polar. Or else it can actually not share electrons at all. It can actually just be ions. And so this is the polarity spectrum. You go from nonpolar to polar to very polar to weakly ionic to strongly ionic. And almost all compounds are going to fall somewhere in there. And again, we treat these types tend to have certain properties and undergo certain types of reactions. And this is the second general class. Okay, let's see what else we want to say here. So we've talked about how you go from non-polar to weak polar to strong polar. I want to just mention something about ionic materials. You can also have something that's weakly ionic or strongly ionic. And there's a good general rule of thumb that we can use to determine that. You just look at the charges of the ions and multiply them together. So sodium chloride, you have one positive and one negative. So 1 times 1 is 1. So this has a relative scale of 1. Okay, calcium is plus 2 and chloride is minus 1. Only consider one of each. 2 times 1 is 2. On the other hand, calcium oxide, 2 times 2 is 4. And calcium phosphate is 2 times 3 is 6. And so just multiplying the charge on the cation and anion will give you a number, and normally the larger that number, the more strongly ionic. Now, let's come back to one more thing, and that is the idea of like dissolves like. It's a very famous saying. So water-based materials tend to dissolve water-based materials and oil-based materials, other oil-based materials, but oil and water don't mix. On the other hand, a salt like sodium chloride readily dissolves in water. How do we explain this? That's where the polarity spectrum comes in. So let's look at this. Water would be, let's say here on the polarity spectrum. This would be water. So water and a hydrocarbon, which is nonpolar, right? Your hydrocarbons, your gasolines are basically nonpolar. They're very far apart. There's a large difference in electronegativity, and so they tend to not mix. But even though salt, sodium chloride, is very different from water, salt is very close to it on the polarity spectrum. And so as a result, water and salt will mix, will readily dissolve. Even though they're very different types of materials, they're very similar in terms of polarity. And likewise, oil and water don't mix because they're far apart, despite the fact that they're both covalent compounds. So here, the idea of the polarity spectrum will really help a chemist determine when something is going to dissolve or interact with something else. And remember, and polarity was based on the fact that the bonding, and the bonding was based on the structure. So all this is tied together. Okay, now let's talk about this, about how to get to polarity and all of the points in between. So I've developed this thing. I'm basically just going to call it the NASA protocol, okay, just to give it a name. But here's what's important about this. If you're given a formula, you should be able to determine some data which can easily be determined by putting that data in table form. And so I call that a NASA table. From that table, and I'll show you an example here in a second, you will be able to determine the Lewis dot structure. Once you know the Lewis dot structure, you can determine the electronic geometry. And once you know that, you can determine the molecular geometry. And once you know that, you can determine the polarity. Here's the deal with this. Each of these is dependent on the other, so it's kind of a cascade. So to get to molecular geometry, you've got to know at least 4 other things, right? To get to electronic geometry, you've got to be able to do at least 3 other things. So in terms of an exam, you've pictured the question gets harder and harder as you move down this list, not because it's much more technically difficult, but just because you have more steps to go through, and the more steps you go through means a possibility of more chances to make an error. So this is the NASA protocol in linear form, and here it is shown to you in graph. And there are a lot of videos that are going to show you how to do this, how to go from step to step. And there's some reminders of some of the things that you want to look for or pay attention to, or that will help you as you work through this cascade. So let me just show you what a practice problem might look like. And here you got sulfur trioxide. All I want to point out here is that you can see the formula there, and you can see there's the formula, and then you can see from there you make the NASA table, and that will give rise to the Lewis dot structure. And from the Lewis dot structure you can determine the electronic geometry, And from the electronic geometry, you can determine the molecular geometry. And from the molecular geometry, you can determine the polarity. And so here's the cascade, and here is a full example. Right. I want to take a quick aside and mention right quick something about the molecular and the electronic geometries. There are only 3 types of electronic geometries, and those are linear, trigonal planar, and tetrahedral, at least in this class, because we're not going to bond any more than 4 things. This is called the central atom, and this is a central atom with 2 elements bonded to it. This is a central atom with 3 bonded to it, and this last thing represents a central atom with 4 atoms bonded to it. There are 2 more electronic geometries, just so you know. So if you look on the lab or you look on Google, don't get confused. There is a structure that has 5. Yes, 1, 2, 3, 4, 5. We're not going to cover that in this class. And there's also a version where you have 6 things connected to the central atom. And we're not going to cover that in the lecture class. So in the lecture class, we're going to limit it to 3 electronic geometries. And those 3 geometries can give you a total of 6 molecular geometries. So from the 3 electronic geometries, you can have your molecular geometries. One of them can be linear, or you can have a molecular geometry that's trigonal planar, or you can have one that's called tetrahedral. But if you take this trigonal planar and you take one of the arms off, you get a bent structure there, so that's called bent. And likewise with the tetrahedral, you can take one arm off and you get this trigonal planar structure, or you can take 2 arms off and you can see you get the bent structure. So those are the 6 basic types of molecular geometry, and they come from the core 3 types of electronic geometries. Right. And these 3, the electronic geometry is said to be symmetrical, okay? And these molecular geometries that are not also in electronic geometry are asymmetrical or lopsided. And if you have a lopsided molecule, it will be polar, and which is kind of working us into the very last piece here. Okay. There are 2 notable exceptions. There's a carbon and an ion, a smaller than carbon, and are an ionic material. So that's a quick fix that you have to put right here. And I just wanted to show you an example where you have an ion. Anyway, you can have a formula, and from that formula you're going to have a NASA table. And from that NASA table, again, you're going to do a Lewis dot structure. And the Lewis dot structure gives rise to an electronic geometry. And from the electronic geometry, you can determine the molecular geometry. And in this particular problem, it didn't ask us to go all the way to polarity, to just stop at molecular geometry. Okay, so there's an example. Right. And the last thing I wanted to mention for this is the amazing water molecule. The difference in electronegativity, polarity, makes these kind of stick together. And also the geometry is important. So this is a good example of where the geometry and the polarity are both important. And it's the amazing water molecule. So there are 2 things that are kind of amazing about this. One of them is the fact that frozen water, ice, actually floats. Most things, when they freeze, it pulls the molecules in closer together, and therefore they're more dense than the liquid form, and the solid sinks. But if ice were more dense than water, all ponds and everything would freeze from the bottom, and basically life could not exist. Everything would just freeze over like Ice Planet Hoth and Star Wars or something. So what is this special feature that makes ice less dense than liquid water? Well, if it's less dense, it means for the same amount of mass, it must take up more space. How is this? Well, let's look at that. Let me highlight some water molecules here, and you can see their shape. And that's one of the exercises you'll do, is determine the molecular geometry. And also, not only that, but they have polar forces that can be in between each of these oxygens and hydrogens, and that holds them into place. And what you'll find out is this whole structure is much larger than if I just took 6 water molecules and let them be in liquid form and just turn about nilly-willy. And so what happens is, because there's some structure to this, to the ice crystal, it will actually wind up, these bridges will make a structure and kind of hold it apart. And so it actually is larger, in other words, less dense than the liquid version. So this is solid, this is ice, okay? And this is water, okay? And you can see that it takes up more volume for the same amount of mass, which means it's less dense. The other thing that's kind of amazing about this is you can see it makes a 6-sided structure. So let me draw the 6-sided structure out here, where this blue represents these 6 sides here. And that's why they tend to grow out this way. They're going to grow off of these. And that's why when you look, all snowflakes are 6-sided, is because they all start with a central interlinked set of 6 molecules.